Let's revise the whole of AQA electric fields. We're going to start off with forces between charges in a vacuum. Imagine that I have a couple of charges. So let's say that this one here is Q1, and let's have another one which is Q2. Now those two charges are a distance r from one another. Depending on whether they're positive or negative, they will either repel or they're going to attract. Let's say that they're both positive for the sake of argument. There will be a repulsive force between them. This means that the charge Q2 will experience a force this way, and the same equal and opposite force will also be present on the charge Q1. The magnitude of this force will be given by a constant, which is conveniently written as 1 over 4 pi epsilon naught. And then we have the magnitude of the two charges, Q1, Q2, divided by the square of the distance between them. Now, E naught over here is known as the permittivity of free space. Its value is given in the formula booklet. It's around 8.85 multiplied by 10 to the power of minus 12. Something important to note is that if one of these charges is suddenly negative, then this force will be attractive depending on the charges. Another thing we need to mention is that this is called the permittivity of free space because this is the equation that applies in a vacuum. However, air can be treated as a vacuum. So I'm just going to write down over here that the air can be treated as a vacuum. One final thing to consider is that if we have some charged spheres, the charge may be considered to act at the center of that sphere. And if we ever need to figure out the distance r will be this distance over here. Let's do an example problem. We have two charged spheres and they're shown over here, and they exert an electrostatic force of attraction on each other. We decrease the distance between their centers by a factor of 2. What will the new force F2 be in terms of the original force F? Okay, so the equation, I'm going to do this I part of this problem over here, is that the new force F2 is simply going to be the product of the two charges, Q1 and Q2, divided by some constants, 4 pi epsilon naught r squared. Now, if r is reduced by a factor of 2, then the denominator of the fraction will decrease by a factor of 4, meaning that the new force will increase by a factor of 4. Because of that, F2 will be 4 times the original force. Part 2, and that new distance, each sphere is given an additional charge minus q. Okay, so this means that the charge on this one is going to be plus 4q, because 5q take away the new charge, minus q is 4q. But then this one here will turn to minus 3q, and then minus an additional one will be minus 4q. Find the new force, yet again, F3 in terms of the original force F. There might be a bit more algebra on this one. So let's write down the new force F3, which is going to be the product of the two charges, which is going to be given by 4q multiplied the magnitude of the other charge, which is also 4q over 4 pi epsilon naught r over 2 squared. It's r over 2 because we are at that new distance, which was half the original distance r. So F3, we're getting somewhere, we have an expression for it, is going to be 16q over 4 pi epsilon naught r over 2 squared. Okay, so how does that compare with the original force F? But we also know that F 2 was, let's do that in a different color, was actually before equal to 5q times that by 3q over 4 pi epsilon naught r over 2 squared, and this was equal to 4 times the original force. Now I'm going to pick a common variable between them. This appears quite a lot in AQA physics, so this could be just the charge q, for instance. 5 times 3, oh, there's a missing square here, really important, let's add that. 5 times 3 will be equal to 15q squared over 4 pi epsilon naught r over 2 squared will be equal to 4f. And now I have a common variable between those two expressions, which is q squared. So shall we just rearrange for q squared, which is going to be equal to 4 over 15, and then I'm going to multiply by 4 pi epsilon naught r over 2 squared, and then multiply that by f. Okay, now let's plug this into here, and we should get an expression in terms of f. So if we were to do that, we're going to get that f3 will be equal to 16 over 4 pi epsilon naught r over 2 squared. Now the 16 will then be multiplied by q squared, and rather than q squared, I am going to write times 4 divided by 15, and then multiplied by 4 pi epsilon naught r over 2 squared, multiply this by f. And look at this, almost all of this is going to cancel out. So the 4 pi epsilon naught r over 2 squared is going to cancel out, and all that we're left with is 16 times 4 divided by 15. So what does that give us if we were to put this into a calculator? As a decimal, it gives us around 4.26 f, which is around, let's call it 4.3 multiplied by f. Let's do another practice problem, a variation of this problem I've seen appear in multiple different forms. So we have a positively charged sphere of a certain mass, 0.25 kilograms, is suspended on an insulated piece of string next to a negatively charged wall. Okay, so this means that those things, the wall and the sphere, are going to attract, meaning that the sphere will get tilted from the equilibrium position to another equilibrium position over here on the left. Find the electrical force of attraction between the sphere and the wall. It's always worth resolving the forces to see what's actually happening in this problem. Now, first of all, there's going to be a downward force due to gravity, which is the weight, and this here will be acting pretty much straight down. Let's call that mg. Now, in order for the sphere to be in equilibrium, the upwards force of tension will have to be equal to that. So the tension can be resolved into two components. Let's call this one, I don't know, let's call that T. This one here could be T cosine of theta. So we can say that the adjacent component, T cos theta, is equal to mg. There's also going to be a force on the sphere, an attractive force. Let's pick a different color for that one, which is going to be in this direction, and that's simply the electrical force. The horizontal component of the tension will act in the opposite direction and will have to be exactly equal to the other one. Let's draw it all the way to the end. It's not really drawn to scale, but this blue arrow has to be equal to that arrow over here. So T sine of this angle here will have to be equal to the electrical force Fe. Even though we can solve this problem quicker without drawing this triangle, a variation of this problem may potentially appear, so I think it's really worth explaining how it works. So because T sine theta is equal to the electrical force, all we need to figure out is essentially our opposite component. We already have our adjacent component because that's just, well, equal to mg. In a way, we actually have a triangle, which is just a 90-degree triangle with the vertical component being equal to mg and the horizontal component being equal to the electrical force. We have the angle here, so we can directly say that the tangent of 40 degrees is equal to the opposite over the adjacent. So tan of 40 will then be equal to the electrical force, I've just called that Fe, divided by the adjacent, which is mg, meaning that the electrical force will just be equal to mg multiplied this by the tangent of 40 degrees. Now, our mass in this problem was 0.25 kilograms, multiply this by 9.81. Multiply this by the tangent of 40 degrees, and putting this into a calculator, we're going to get around 2.057 newtons. Shall we just call it 2.1 newtons. And now let's compare the gravitational and the electrostatic force between subatomic particles. We need to find the ratio of the electrostatic repulsion to the gravitational attractive force. So the easiest way is just to draw a little line, because remember, ratio is just division. So at the top, we're going to have the electrostatic repulsive force. I'm just going to call that Fe. At the bottom, I'm just going to write F subscript G for the gravitational force. So my repulsive force is going to be given by the magnitude of the two charges. They're going to be the same, but let's just write Q1, Q2. And then we're going to be dividing that by 4 pi epsilon naught r squared. And then at the bottom, if you remember, the law for gravitational attraction is equal to m1, m2, multiplied by the gravitational constant g, divide that by the distance between them, which is r squared. The factor of the distance, 1 over r squared, is going to be the same for both of these, so that can be cancelled out. Okay, let's plug in some numbers. The charges and the masses are going to be the same. So just the denominator of this fraction is going to be Q1, Q2, which is 1.6 times 10 to the power of minus 19. This is the charge of a proton, and it's 1 multiplied by the other, so that's why I'm going to square it. Then we're going to be dividing that by 4 pi times by epsilon naught, which is 8.85 times 10 to the power of minus 12. So this here is just the denominator of our fraction. Then we need to divide by gm1, m2. So because it's two protons, it's just going to be 1 over, multiplied by 1 over. The gravitational constant g is 6.67 times 10 to the power of minus 11. And then the mass of a proton, if memory serves me right, it's around 1.67 times 10 to the power of minus 27. And there's two of them, so we need to square it. Plugging this into a calculator, we're actually going to get an enormous number, somewhere around 1.237, let's call it 1.2, multiplied by 10 to the power of 36. The electrical force is orders of magnitude larger than the gravitational force. Now we're going to have a look at representing electric fields by electric field lines. Now, first of all, what is an electric field? Well, it's simply a region of space. If we were to place a small positive test charge, for instance, if I was to place right over here a small little proton, like a small positive test charge, next to this positive charge, it will experience an electric force. The electric force along here will actually be in this exact direction. Because it's repulsive, it will be to the right. Now, the electric field lines show that direction. They show the direction of the force / acceleration on a small positive charge that's been placed in the field. I'm just going to underline the word positive because that's really important. That's how we define the whole of electric fields in terms of positive test charges. Drawing the electric field lines is very, very similar to gravitational field lines. However, they can be positive or negative because the force can be both attractive or repulsive. If the charge is negative, the field lines go into the negative charge. If it's positive, they come out of the positive charge. Because of that, we can also say that the electric field lines always go from positive to negative. What are some other rules for their drawing? Well, they enter and leave surfaces at 90 degrees. The density of the field lines means a higher electric field strength. For instance, if I was to have a charge, let's say plus something, but the field lines were so much denser, then this would mean that the electric field strength at around that charge is higher, meaning that probably there is more charge right over here. If I had a positive charge next to a negative charge, we can just follow all those rules. First of all, between them, the electric field will be going from positive to negative, and following this rule that they enter and leave surface at 90 degrees, the field line is going to leave the positive charge, it's going to curve away, then it's going to enter at 90 degrees. And right over here following this one, it's gonna leave at 90 degrees, curve away, and then enter always from positive to negative at each point. If they were both positive, the field lines will end up cancelling between them. Why is that? Because there will be a field line coming from here in this direction, one from there in this direction, and they're both in the same direction, so they end up cancelling each other out. Another type of question that appears is a charged sphere next to a wall. We just follow the rules. Field lines go from positive to negative. They leave at 90 degrees and they enter at 90 degrees at pretty much all the points. And now let's talk about electric field strength. This here is a really important definition. Electric field strength is defined as the force per unit charge on a small positive charge. This is typically a 2 marker with 1 mark going for the force per unit charge and 1 that it acts on a small positive charge. There are several equations which we can express this definition with. The first important one, and that is the main electric field equation, is that electric field strength is equal to the amount of force divided by the charge. Now, in this equation, Q is the charge which experiences the force. Another really important equation is for radial fields. Since the electric field strength is equal to F divided by Q, if we remember, the electrical force is equal to Q1, Q2 over 4 pi epsilon naught r squared, and then we need to divide by Q, so we're doing 1 divided by Q, where Q is the force that is the charge that experiences the force. Now these are going to cancel, and what we're left with in this case is just Q2 over 4 pi epsilon naught r squared. Now Q2 is in this case the charge which creates the field, or the charge which is the source of the field. The index is actually typically removed, so people tend to, in general, just write that the electric field is given by Q over 4 pi epsilon naught r squared. This only applies for a point charge or for a spherical charge, essentially for radial fields only. On the other hand, E is equal to F over Q can be applied for any electric field out there. There are a couple of different units that we can use for electric field strength. For now, because electric field strength is equal to force per unit charge, force is measured in newtons, charge in coulombs, so the unit we could use is newtons per coulomb. You also see later on, because of a different equation in uniform electric fields, we could also use volts per meter. Now, what about the base units? Well, because force per unit charge can also be expressed as mass times acceleration divided by charge, which is just current multiplied by time, we could say, well, the units of mass are kilograms, the units of acceleration are meters per second squared, the amp is a base unit, and the second is also a base unit. So what we're going to get is kilograms meters. S to the power of minus 2 divided by S is going to give me S to the power of minus 3. And we also have A to the power of minus 1, which is the base unit of electric field strength. Another example problem on electric fields. We've got two charged spheres and they're 1.2 meters apart. Well, their centers are 1.2 meters apart. Find the distance d at which the electric field between the two charges is 0. And d is measured from the 2.36 Coulomb charge. So let's just say, for the sake of argument, that this is the distance here. Let's draw it in a different color. I.e., this one here will be d. So at this point, there's going to be two electric fields and they should be equal and opposite. In practice, one of the electric fields will be from the 2.36 Coulomb charge, which is positive, and then there's going to be another one from the 5.73 charge, which is also going to be equal and opposite. And the two will have to be equal in magnitude. So we can call one of them, I don't know, E1, the other one E2. We can say that E1 is equal to E2. Because we're dealing with radial fields, we can say that Q1 over 4 pi epsilon naught R1 squared. Now, what would the distance actually be? So the distance from the first one will just be d, so we can say d squared will be equal to q2 over 4 pi epsilon naught. Now, the distance from one of them to the center of the other is going to be 1.2 take away d. So we're going to have 1.2 take away d, and then all of this is squared. Okay, without even plugging in the numbers, I'm going to do a bit of cancellation. So 4 pi epsilon naught can go. And what we want to do is isolate the distances on one side. Okay, so let's just do a bit of rearranging and see what we get. I'm going to say that Q1 multiplied by 1.2 take away d, all of it squared, is going to be equal to Q2 multiplied by d squared. This looks like it's going to be a quadratic, so shall we just do expand the bracket? So 1.2 minus d squared, what is that going to give me? That's going to give me 1.2 squared minus 2 times 1.2, which is 2.4, multiply this by d, and then plus a factor of d squared. And this here will be equal to Q2 multiplied by d squared. Now we can probably plug in the numbers because Q1 is that and Q2 is 5.73, and set up a quadratic. So we're going to get 2.36, multiply this by 1.2 squared, take away 2.4 d plus d squared will be equal to Q2, which is equal to 5.73, multiply this by d squared. I'm going to set up the quadratic over on this side. Now we can bring the factor of minus 5.73 d squared essentially on this side, or the factor will become minus that. So this here is going to give me minus 5.73 plus 2.36. This here will be our A. d squared, then minus 5.664d, and then plus 3.3984 is equal to 0. And now we can apply our quadratic formula. Remember, the quadratic formula is given in your formula sheet, so our x, or indeed our distance, will be given by minus b. So what is that going to give me? 5.664, and then plus or minus the square root of b squared, which is 5.664 squared. Take away 4ac, so plus, because it's minus a, so 4 times a, which is 3.37. Multiply this by c, which is 3.3984. And we're going to divide all of this by 2a. So it's going to be minus 2 times 3.37. Now, one of our solutions is going to be between the actual spheres. So one of them is 0.46908. So should we just call that 0.47 meters? This actually makes sense. I should have picked the point closer to the first sphere, because the relative electric field strength of the first sphere is a lot smaller than the second sphere. The second solution, D2, is around minus 2.1 meters. Well, this is not between the spheres, so we can actually discount this. It's also not a physical solution because the electric field strength of the 2.36 charge, if we go on the other side of the sphere, will end up changing its direction. Now we'll be going to the left rather than the right, so we can completely ignore this solution. Another type of problem that appears quite often is a geometric shape with some charges on it. So for instance, we're given a circle and we need to figure out the resultant electric field at the center of the circle if the radius is 0.5 meters. So first we need to look at symmetry. Now, we've got a charge +5 and a charge +5 here. The field between them will consist of a field line from this one that's going to be going this way, and a field line from the other one that will also be going the same way. And those two field lines will be equal and opposite. So that means that the +5 Coulomb and a +5 Coulomb charge will end up just cancelling one another. So in a way, we can just cancel out those two charges. If we have +5c here and +5c here, well, the effect will be the same, because through the center there's going to be a line coming out this way, and there's going to be a line coming out this way. So those two will essentially cancel out the effect of one another. So the problem is now greatly simplified, because all we need to do is figure out the charge from this 5 Coulomb charge, the electric field from there, and one from the 3 Coulomb charge. This 5 here almost doesn't look like a 5. Shall we change it? That's a little bit better. So those two are meant to be diametrically opposite and to go right through the center like this. From the 5 Coulomb charge, there's going to be an electric field, should we just call that E1, which is going to be going this way. And then from the 3 Coulomb charge, there's going to be an electric field, shall we draw this one in red maybe, that's going to be going the opposite way, because electric fields come out of positive charges and those two are both positive. So now we need to take away E1 and E2 because geometrically they're going in the opposite direction to find the resultant electric field strength. So E1 take away E2 will be given by, let's call it Q1 over 4 pi epsilon naught. R squared take away Q2 over 4 pi epsilon naught R squared. Now R in this case is going to be the distance from the charge to that point, which is just going to be the radius of the circle. So this here is just 0.50 meters in both of these occasions. Okay, so Q1 is 5 over 4 pi 8.85 times 10 to the power of minus 12. Multiply this by 0.50 squared. Take away Q2, which is 3 over 4 pi 8.85 times 10 to the power minus 12 times 0.50 squared. And this here is going to give me a very large electric field, which is 7.2. Multiply this by 10 to the power of 10 newtons per Coulomb. Now let's have a look at uniform electric fields. First of all, what is a uniform electric field? Well, have a look over here. We have two parallel plates, one positive and one negative. The field lines are just going from positive to negative. Well, the field lines are also equidistant, meaning that they're the same distance apart, meaning that the electric field strength is the same anywhere between those two plates. There's a special equation which we only use for uniform electric fields, and that is that the electric field is equal to the voltage between the plates divided by the distance between them. We also need to be able to derive this from work done moving a charge between the plates. How do we actually do this? Well, remember that work done is equal to, in general, to force multiplied by distance when the force is perpendicular to the direction of motion. However, work done in moving an electric charge is equal to the magnitude of that charge, Q, if we were to move a charge, let's say Q from one plate to the other, and then multiplied by the change in voltage, or the voltage gap between them, which is just the voltage between the plates. This here will just be equal to force multiplied by distance. We can rearrange this a little bit, and we can say that delta V over D, basically I've just brought the voltage onto the left-hand side, and I'm going to bring the charge from the left-hand side onto the right-hand side, will be equal to F divided by Q. However, force divided by charge, or the force per unit charge. Remember, the magnitude of the electric field strength is just equal to force divided by charge. So this entire left-hand side is just the electric field. So we know that the voltage gap divided by the distance is equal to the electric field. And this is where the equation that electric field is equal to voltage over distance actually comes from. V is just the voltage between the plates, in other words, the voltage gap. Let's do a practice question. We have a charged particle that is placed somewhere between two parallel plates, which are separated by a distance d and have a potential difference of v between them. The charge on the particles is Q and its mass is m. Show that the acceleration of the charged particle due to the plates is given by... Okay, because this is a show question, let's underline this command word. I'm going to try and give quite a lot of steps. In order to work out the acceleration, I am going to need the force, or the net force acting on it. Typically in those problems we tend to ignore the effect of gravity unless otherwise specified in the problem. So we can say that F net is equal to mass times acceleration. But remember, the electric field strength is equal to F over Q, meaning that F is equal to E times Q. So E times Q will be equal to MA, meaning that A will be EQ over M. Remember though that the electric field is equal to V over D, so this here is going to give me VQ over DM, which is exactly what we have over here. And now let's do a problem which does not ignore gravity on purpose. So show that the voltage required to keep a particle of mass M and charge Q stationary between two parallel plates with potential difference V and distance d is given by the following expression. If you want to keep the particle stationary, we are going to need an upwards force which balances out the weight. So let's say the electrical force is just F. This is going to have to be exactly equal to mg, which is acting downwards. So we can say F has to be equal to mg, but remember F is just equal to E times Q, which is equal to mg. The electric field is V over d times Q is equal to mg. V will be equal to mg. Bringing the d onto the other side, we get mgd. Divide that by the charge Q, and those seem to be identical. Now let's have a look at the trajectory of moving charged particles entering a uniform electric field, initially at right angles. Now, what on earth does that mean? Well, if we have two parallel plates, one positive and one negative, let's say that we have initially an electron, so a negative charge particle entering. At the moment this electron enters over here, it's going to experience a force. The initial force will be towards the opposite plate. So if this here was an electron, there's going to be a force acting on it, a constant force given by EQ, which will be acting towards the positive plate. Because there's a constant force acting, then the electron will start curving towards that plate. Depending on its initial speed, it will either get absorbed by the plate, or if it has a fast enough velocity, it might be just a very slight curve and might just escape. On the other hand, if we had a positive particle, so let's say something like a proton, at the very moment that it enters, it's going to be attracted towards the negative plate, where it also gets repelled by the positive plate as well. In other words, it will go along the field line and it will get curved towards the negative plate. And once again, depending on the initial speed, if it's moving really fast, this might be just a very, very slight curve and it might escape. But either way, it will be a curve towards the opposite plate. Now let's do a practice problem. We have an electron that enters a region of two parallel plates with a potential difference of 3000 volts. So the electron enters perpendicularly to the field. That means purely horizontally in this context, with initial speed of 1.5 times 10 to the power of 7 at the midpoint between the plates. Okay, we're given the distance between the two plates, which is 25 centimeters. So this means that this distance here will end up being 25 centimeters over 2, and so will this one here. The length of the plates is 50 centimeters or 0.5 meters. Does the electron manage to escape the region of the electric field before it collides with the positive plate? We need to support our answer with calculations, and we can ignore the effects of gravity. The first step in solving these problems would be to work out the acceleration. So remember, the force as soon as we enter the electric field is given by EQ. In other words, MA is equal to EQ. The acceleration will be equal to EQ divided by M. The electric field is the potential difference between the plates divided by the distance between the plates and multiplied by the charge. Okay, so the voltage between the plates is 3000. Because it's an electron, its charge is 1.6 times 10 to the power of minus 19. The distance between the plates is 25 centimeters or 0.25. It's important to use 0.25 because the electric field is the same anywhere. It's given by the distance between the two plates, which in this case is a constant. Okay, multiply this by the mass of the electron, which, if memory serves me right, 9.11, 10 to the power of minus 31 kilograms. Putting this into a calculator, we get around 2.1 multiplied by 10 to the power of 15 meters per second squared. Okay, so this here is the vertical acceleration. The electron will end up being attracted towards the positive plate along here, and the question is it going fast enough to leave the surface? Well, let's figure out how long it actually takes for the electron to strike the vertical surface. So this distance here will just be given by 0.125 meters, which is just half of it. So we can work out the time for it to strike the vertical plate just using suvat. So I can say that in the vertical direction, the vertical displacement, let's call it Sy, will be equal to the initial speed in the vertical direction multiplied by the time plus a half at squared. Now, initially the velocity was purely horizontal, so we can essentially get rid of this term. We know what the displacement will be. It's just 0.25 over 2 because it was at the midpoint. A half, we know that. We've just worked out the acceleration. We can just literally rearrange for t, meaning that t will be the square root of 2sy, that's the vertical displacement, divided by the acceleration. Okay, let's plug in some numbers. So 2 times 0.125 divided by the acceleration, which is very large, 2.1 times 10 to the power of 15. And this here is just a very small number, 1.09 multiplied by 10 to the power of minus 8 seconds. Okay, so we have the time of flight. This is essentially projectile motion, but rather than gravitation, we have a very strong electric field, which gives us a much higher acceleration typically. Now that we have the time of flight, we can focus on the horizontal direction. It's important to note that because when the electron is here, the only forces that act are in the vertical plane. So this means that the horizontal component will remain exactly the same. So the horizontal speed at all times will be equal to the initial, which was 1.5 times 10 to the power of 7 meters per second. That remains constant. So how much distance will it cover in that time? Well, because the speed is constant, let's say that it travels a distance x. We can say that x will be equal to the initial horizontal speed, let's call it ux, multiplied by the time. So our speed was 1.5 times 10 to the power of 7 meters per second, multiplied by the time, which is 1.09 times 10 to the power of minus 8 seconds. And we actually get an answer of 0.1635, let's just call that around 16 centimeters. So the answer is no, the electron will collide with the positive plate only at a distance of 16 centimeters. So the trajectory is going to be quite aggressive. So let's say that 16 centimeters is somewhere here. It's probably going to do something like this. And now let's talk about the electric potential. The definition of the electric potential is that it's the work done per unit charge to bring a positive charge from infinity to a point. And we can agree that the electric potential is 0 at infinity. An alternative definition, typically accepted in the mass schemes, is that it's the electric potential energy that a unit positive charge will have at a point. There is a distinction between potential difference and the absolute potential. So the formula for the absolute potential for a radial field is that the electric potential is going to be given by 1 over 4 pi epsilon naught, assuming that we're in a vacuum, multiplied by the charge divided by the distance. If we're looking at potential difference, typically we're looking at delta V, which is the change in this quantity. If we wanted to move a charge in some sort of an electric field, this would require some work done typically. And the equation for the work done, let's call that delta W, is that delta W will be equal to the charge multiplied by the change of potential. Now we can actually use that to get a formula which is not actually on the formula sheet, but if we take one of those references to be infinity where the potential is 0, change in V can just be equal to V. So we can say that electrical potential energy, let's say we had two charges Q1 and Q2, can also be given by Q1 Q2 over 4 pi epsilon naught multiply this by R. This is if we're moving one of those charges in the presence of the other one. Let's apply this to an example problem. We've got a potential given between 2 points 1 and 2. How much work does it take to move a 10 millicoulomb charge from point 1 to point 2? So we're just going to use W is equal to the amount of charge times by the potential difference. So my charge is just 10 millicoulombs, so 10 times 10 to the power minus 3, and my potential difference, delta V, is just going to be 200 minus 50, so it's going to be 200 minus 50, which is plus 250, so this is 10 times 10 to the power of minus 3, multiply this by 250, which is just going to give me 2.5 joules. In terms of the graphical representations of the potential with distance, we're going to have a couple of variations. So for a positive charge, the variation will look something like this. It's similar to the equation y is equal to 1 over x. Why is that? Because v is equal to the constant 1 over 4 pi epsilon naught q over r. Basically, you have v being inversely proportional to the distance, and somewhere at infinity this starts tending towards 0. So on the other hand, if it's a negative charge, it's gonna look something like this, once again approaching 0 as r tends towards infinity. We can figure out the electric field strength at any point just by using the gradient of the tangent. We could figure out the tangent at this point, so something like this. Mathematically, in thinking about units, if we take v and we divide it by an infinitesimal r, in reality we're actually differentiating, but you can think about this as dividing small quantities of one over the other. We are actually going to get units of q, which is the potential, which is the charge, 4 pi epsilon naught r, which is the potential, divided by r again, we're going to get q over r squared. Well, remember, this here is just the electric field strength. Mathematically, we would write this really importantly as electric field strength is equal to the change of potential over the change in distance. Now, sometimes I've found in questions that this delta R could be disguised somehow. For instance, you could have the variation of the potential difference against height from the ground or something like this, and you may have to figure out the electric field strength by finding the gradient of a tangent at a point. Sometimes you can also come across a graph such as this one. You have the electric field strength against distance. Well, we could do the reverse. We can pick 2 points, let's say point 1 here and point 2 here. Then we may need to estimate the area of the graph. And if that's the case, the reverse of it, the area is equal to the potential difference. Area will be equal to the work done per unit charge to move from one point to the other. Let's cover equipotentials as well. So imagine we have some positive charge, we'll just call it plus Q. What do the field lines look around that charge? Well, they're going to be radial lines coming out of the charge. So equipotentials are lines where the electric potential is the same. The potential around a point charge or a sphere is going to be the same around a circle centered around the charge. So if I was anywhere along this circle, I would be equidistant from the charge and the potential will be the same. Or if I was anywhere along here, the potential would also be the same. There are infinitely many equipotential lines. Important to remember some rules. Equipotential lines are perpendicular to field lines, and no work is required to travel along an equipotential line. Just a little note that the spacing between the equipotential lines represents the relative strength of the electric field. So because the strength of the electric field is decreasing as we move away from the charge, the next one would be somewhere quite a bit further apart, or something like this, but centered near the surface. That will tell me that the field is actually decreasing with distance from the source. And let's do another practice problem. What is the change of electric potential energy when a proton is moved from position 1 to position 2, which is directly below? The electric potential energy is going to be the same anywhere along this vertical line. Well, how do we know this? Imagine if we were to release a proton from anywhere along this line, it is still going to strike the other surface with exactly the same speed because it will have acquired exactly the same amount of energy. So anywhere along this line, we're going to have the same electric potential energy. So the answer to the first question is actually 0. What about from position 2 to position 3? The distance between the points is 15 centimeters. Okay, well, the work done will be equal to Q multiplied by delta V. The question that we need to find is what is the potential difference between points 3 and 2. And we know that this distance here is 15 centimeters. Okay, we're given the distance between the plates is 0.5 meters. So the trick with this is to find the electric field, which is equal to V over D, which is going to be 100. Divide that by 0.5, i.e. this here is going to be 200 volts per meter. So what potential difference are we going to cover in our journey of 15 centimeters? Well, because V is equal to E multiplied by the distance, we are going to take 200 and then we're going to multiply this by 15 centimeters and we're going to get around 30 volts. Okay, now we're ready. We know what our delta V is. We can just plug that into here. So we can say that W is going to be Q delta V. The charge of a proton is 1.6 times 10 to the power of minus 19. Multiply this by 30, which is going to give me 4.8 times by 10 to the power of minus 18 joules. Well done for revising the whole of electric fields. What you should revise next is capacitors, and this is precisely why you should click on this video where I go over the entire AQA syllabus on capacitors. Click over here.